everybody. I hope everybody's having a wonderful day. So I'm going to be picking up from where we left off last time. So first, I want to remind you of the definition of big O because we're going to be using it throughout this lecture. So remember that F is big O of G, if and only if. So it means whatever's here is logically equivalent to whatever follows that only if here. There exist constants, which are a positive real number C and a positive integer n0. So both of those are constants, such that for n is greater or equal to n0, f of n is less than or equal to c times g of n. So I'm just going to pick up the example I did last day. Now remember, I just did a chart and I found c and n0 that would fit the definition of big O, but you're going to find that that isn't really, like, just drawing a picture isn't sufficient as a type of mathematical proof or some easy way to convince somebody when I give you an arbitrary function. I'm going to show you where I can kind of push this a little bit. I just want to illustrate this, and then we're going to do a few examples, then I'll show you one other thing after this. So I'm just going to consider what I did last day. So I have f of n is equal to 2n, and I have g of n is equal to n squared. I'm going to show 2n is big O of n squared. So what's the game plan? So I like to lay out the game plan for which we're going to try to prove these claims. So remember, the definition says that there exist constants, c and n0. So remember, c has to be a positive real constant, and n0 has to be a positive integer. That means 1, 2, 3, 4, 5, up as big as you need. Not 0 though, because it has to be positive. The same thing here. C can't be 0. It has to be some, you can think of it as rationals or irrational numbers, as long as it isn't 0, but they have to be positive, okay? So we need to find these two constants such that when I plug those two constants in, it has to be true that for all n greater or equal to that second constant, n0, this inequality holds. So that's the game plan. So whenever I do this, I always lay out what I need to do. So I need to say we need to find a positive real constant c and a positive integer constant n0, such that for all n greater or equal to n0, 2n is less than or equal to cn squared. Okay? See, that's not too terribly bad. So remember, I've just laid out what exactly I want to do. And now we're going to do a little bit of massaging here, and we're going to see what we're going to get. Now, my strategy, this is my personal way of doing things. You don't have to do it this way. I find it very easy to pick c and then find n0. That tends to be a pretty typical pattern. You can also do it the other way around, where you pick n0, then you find a c. Remember, I just need to find a c. Likewise, I need to find n0, right? I just need one. I don't have to tell you every possible one, just one of each. So, what I'm going to do is I'm going to pick a constant. Now, I'm going to kind of motivate why this is not the most ideal constant to pick, but it works. So I'm going to pick c is equal to 1. This is actually the one I used last day. Remember, you saw the chart, it worked fine. Let's pick c is equal to 1. So, we need to find n0 such that for all n greater or equal to n0, 2n is less than or equal to 1 times n squared, right? That's what it says. So now I just got to find n0. So if you want to go back to some earlier mathematics you may have done, if you're given something like this and it looked like instead of an inequality where I have less than or equal, imagine if it was equal. I want you to just imagine if this was equal and you were trying to solve this. What would be one of the first things you would try to do? You might try to solve for roots. So I'm going to try that out. So let us try finding the roots. Assuming equality. So I'm just going to pretend that less than or equal is an equal sign. So let's do a little bit of algebra. First, now Sometimes I find it a little easier to work with if you just keep f and g in their base form, so I'll just do that here. So first, f of n is less than or equal to 1 times g of n. If and only if and only if. Now I'm just going to pull g of n over to the left-hand side by subtracting on both sides. Actually, sorry. No, let's move f of n to the right-hand side. I think that will work a little bit better. You got to think about these things. You're going to find that not every time it's going to work out where it's going to be very simple to see what you're going to do. So I'm just going to rewrite that a little bit. So I'm just going to subtract f of n on both sides. So now I have g of n minus f of n is greater or equal to 0. Then, don't forget a period. Remember, we got to treat these things like sentences. One thing I want to suggest is don't just write blindly inequalities like this. Remember, you want to say words that connect the pieces you're trying to approach this with. So for example, I say I'm going to try solving for something, right? If I wrote this just blindly, I wouldn't be telling you if the statement's true or false or what I'm going to do with it. So you're going to find very often that you want to attach words to the things you're doing. Otherwise, somebody could misconstrue what you're writing. So don't just write inequalities like this. You need to have words that connect the pieces. Then, putting f and g in, so substitute f and g in, then I get n squared minus 2n is greater or equal to 0, which simplifies to simply n times n minus 2 is greater or equal to 0. So you'll notice that all I've done is I'm just factoring out the additional factor of n here. So now I have n times n minus 2. So what does that mean? So when is this inequality tight? That means when is this equal to, in fact, 0? This one right here, which would imply, of course, the original one up here. Well, there's two possible solutions here if I assume that greater or equal sign was, in fact, a less than or is an equal sign, sorry. What you would do is, okay, well, what do you do? Okay, now think of these as two different factors. Okay, well, if I make this one 0, the whole thing on the left-hand side is 0, so we're good there. How about the other one? How do I make this 0? Well, I just make n equal to 2, right? When n is equal to 0 or n is equal to 2, the inequality is tight. I'll use that in quotation marks, because I haven't really defined what tight means. So, what do you do usually when you deal with things like this? Okay, remember, I want the furthest along n0. I want the biggest of these two, right? Remember, when I drew my picture, I wanted the place for which g of n started beating f of n. It started dominating it. Well, it happens at the furthest of these 2 points, right? Because we know how a quadratic behaves versus a linear function behaves. So this is one implicit assumption we're making when we say this. So we want f of n is less than or equal to c times g of n, which is just equal to g of n, right? So select n0 is equal to 2. Now, if I pick this one here, it must be because this inequality this width equality was true when it was 2. If you tried looking at this, now remember, I'm just assuming the behavior of linear versus quadratic functions when I talk here. These are the kinds of assumptions I'm okay with you making in this course. So for example, things like n is less than or equal to n squared, or log n is less than or equal to n. These are things I think are reasonable assumptions that I can make for certain values of n in this course. You don't have to pull out some crazy analysis. There's only when it gets a little bit more complicated than that do we really need to pull that out, okay? So basic functions like this, I'm not too terribly worried about. But you need to show your work, right? You got to show your reasoning. So select n0 is equal to 2. For n greater or equal to 2, g of n minus f of n is greater or equal to 0, which implies f of n is less than or equal to g of n. I removed the 1 because it just seemed kind of meaningless. Therefore, by selecting c is equal to 1 and n0 equals 2, it follows from the definition of big O that what does it imply? What does it imply? There goes my eraser. That was a big thud. What does that imply? We found these two constants, right? And they work. So we're done, right? So it implies that by definition of big O that 2n is big O of n squared, right? Now, what if you chose a different constant? So that concludes this example. Okay, so what if I picked a different constant for c? Would this be easier or harder? Are there certain values for c that will work and ones that don't work? I want you to think about this. What I want you to try is try this example again with c is equal to 2 and see how it goes. You might find this root approach not very neat. You don't need something like this. I'm going to show you a technique that's much, much easier to use, and you're going to find it almost standard. So let's do another example. We're going to show n plus 5 is big O of n. Okay, so here's my proof of this. So I'll just write solution, just because it makes things a little easier. Remember, I always write what I'm going to do. We need to find constants c, which is a positive real number, and n0, which is a positive integer, such that for all n greater or equal to n0, n plus 5 is less than or equal to c times n, right? This is g right there. That's n. So I want you to think about constants that might work here. Now, I want you to think about it. I'm going to pick c is equal to 2 here. So I'm just going to say pick c equals 2. Then we need to find n0 such that for all n greater or equal to n0, n plus 5 is less than or equal to 2 times n. So let's think about it. I have this inequality in play. I'm going to try to massage this inequality using a little bit of algebra and see if I can make this simpler so I can determine the appropriate value for n. So I don't want to use this root approach typically. Like, it is one strategy you can use, but it relies a lot on my understanding of how the functions behave beyond the roots. Likewise, it tends to work well when you have a finite number of roots, right? So let's see here. So if I have this in play, what I'm going to do is I'm going to subtract n from both sides. So from both sides, i.e. I'm going to move n from the left-hand side to the right-hand side. Then 2n is greater than or equal to what? N plus 5. So I've just flipped this around a little bit, just rewrote it. If and only if, so this is me actually applying this if and only if and only if n is greater or equal to 5. Notice all I did was I took this expression here, and what I did was I just subtracted n from both sides, and look what happens. Well, n is gone from this side, and all I end up with is n is greater or equal to 5. Well, what's an appropriate value for n? Now, I remember this is just a valid algebraic operation, so if this is true, then that one has to be true. So what should n0 be? Usually you want to pick the smallest one that works, if you can. It's not very interesting if I pick n0 is equal to 10,000. That's not, you don't want to be doing that, unless that is indeed the smallest possible one, or a reasonably small one. You want to find one that isn't just you just kind of throwing a dart at a wall and just saying, that might be big enough. That doesn't give us much insight. Remember, I still want to know when one algorithm might be doing better than another algorithm, okay? So sometimes this n0 can be somewhat helpful, at least intuitively. So choose n0 is equal to 5. Therefore, now I just need a conclusion. So I'm always going to have a conclusion here. Therefore, by the definition of big O, n plus 5 is big O of n. See, isn't that pretty cool? Now, I'm going to take it one step further. Okay, so I want you to notice that in this case, when I picked c is equal to 2, I had it so that I got n big enough on the one side of my inequality such that I could subtract off an extra n to eliminate all the possible terms on the other side of the inequality. You're going to find that this generalizes really nicely. And I'm going to show you an example of why I mean by this. So when you have things that look like polynomials, this is going to be a pretty standard trick that you will like to use. At least I recommend it. It's pretty nice. So you don't need to throw out as many more tricks like root solving and so on. But you should be aware that you can also use solving roots, but you have to know things about the functions to be able to do that properly. This, however, is pretty easy once you realize the trick. So show that 3n squared plus n is big O of n squared. So what's the first thing we do? We say what we're going to do, right? What I call the game plan. So this is just what I call it. Somebody else might call it a strategy, how I'm going to prove the claim. So we need to find constants C, remember it's a positive real constant, and n0 is a positive integer constant, right? Find constant C and n0 such that for all n greater or equal to n0, 3n squared plus n is less than or equal to c times n squared. So that's what I want to show, right? I need to find the c and the n0 such that this works. So here's the trick that I want to kind of impose on you as an idea. So it's going to generalize the strategy I used in the previous example here. What I want you to do is imagine I have 3n squared plus n squared. What would be an ideal constant if it was like that? Well, if this was 3n squared plus n squared, remember it's n, but we're imagining this as n squared here. If I were to make c is equal to 4, you'll notice that 3n squared plus n squared is equal to 4n squared, right? Well, maybe we should use this strategy because notice that n is less than or equal to n squared. Do you see what I mean? I can use a strategy quite similar to this one over here, but use it more broadly over many terms. So, that being said, what is the constant you want to pick in this example? I want you to look at this look at your screen and try to hold up a number that you think that constant is going to be. I'll give you a tip. A nice easy constant is 4. There's other ones that work, but 4 I find is a really nice constant. So I'm going to pick c is equal to 4. So I selected c, now I just got to find n0, right? So I say then we need to find n0 such that for all n greater or equal to n0, 3n squared plus n is less than or equal to 4n squared. So now here's this is how it's going to generalize really nicely for us. Notice that, and remember this is my justification, you can't just omit this. Notice that 3n squared plus n is less than or equal to 3n squared plus n squared, which is equal to 4n squared, which is equal to cn squared, right? For all n greater or equal to 1 as the following. 3n squared is less than or equal to 3n squared for all n greater or equal to 1. And n is less than or equal to n squared for all n greater or equal to 1, right? So you would agree with me that if I took these two inequalities, this 3n squared is less than or equal to 3n squared, and I took this n is less than or equal to n squared, if I sum these two inequalities together, I'll get this one, right? So if this is true here, and this is true there, then it must be true up here as well, okay? So this is my justification for how I can justify what I'm doing. So what's n0 now? Well, I can pick n0 is equal to 1, right? Now, I must stress, n0 can't be 0 because, remember, n0 must be a positive integer. Likewise, you can also pick other n0 values. So, for example, n0 is equal to 2, works perfectly fine. 3, 4. The point is that the smallest one for which this constant works, and it's nice and clean, is n0 is equal to 1. So I'm just going to write that. So I'm just going to say choose n0 equals 1. Therefore, by selecting such C and N0, what do I need to say? What do I need to say? If I pick such a C and N0, what does that imply? What follows from that? What follows, everybody? We get our conclusion, right? Because I found C and N0, which are the ones in my definition. So I say therefore. So remember, I need my conclusion. Therefore, by selecting such a C and N0, it follows from the definition. Of big O that what? 3n squared plus n is big O of n squared. And we're done. That's it. Wonderful. Isn't that not too bad? So the big thing I want you to observe is that all I did here with the way I selected C, now this approach typically it's nice to pick C in a nice intuitive fashion. So the whole trick I used is I looked at what my F is. So this is F right here, and this is G. If I can take each one of the coefficients of my polynomial like this, so I picked 4 because if you look at this, okay, 3 plus 1 is equal to 4, right? So this makes it big enough over here so that I can invoke some reasoning like this. Does that make sense to everybody? So that's the general strategy you can use involving polynomials like this. It's a very nice technique. So the whole idea is just to make your constant big enough so that you can take each of the terms of F and compare it against pieces of G. So what I mean by pieces, I can decompose G into the different parts, and then I can say, okay, well, if I add them all together, we're done. See, it's not too bad. In the notes, I have one more example illustrating this, so take a look at that. That's, I believe, example number 3. So I'm going to switch gears, and I'm going to talk about showing that F is not big O of G. So I've shown you how you can take something and say, hey, look, F is big O of G. I want to show you how you can show that F is not big O of G. Sometimes you really want to say, hey, look, this function that's just too big, right? It's too big. It's never going to dominate the other one. So G is never going to say, come along and start dominating F. This is not going to happen in this case. So here's how we derive the definition here. All I do is I logically negate the definition of big O. Now, you may not know how to negate logical statements, but you'll find that I'll give you a really intuitive way of looking at this. I'll show you a couple of different ways you can go about this. We can also use the definition of big O. The definition of big O to say F is not big O of G. How? How do we do that? We negate the definition of big O. That is, so I'm going to write down the negation. Now, don't let this thing scare you. It's a little bit of the dreaded M word. That dreaded M word. Don't let it. It's not too bad. So, F is not big O of G if and only if if and only if. Now, in my original definition, I had to find two constants, right? C and N0. Now, intuitively, you found those because you imagine all those constants, and you're like, okay, well, each one of those is like our CPU cycles, so different machines might have different speeds for the instructions, and there was this point N0 where one of the algorithms dominated the other one. So anything after that, this one that was in the big O will start doing better, right? So, that being said, I'm getting a little bit tongue-tied here. The point I'm getting at is that you had the C and the N0. You found them. That was the game plan. Now, I want to show you that there's no possible way you can select C and N0. So that's what our game plan is going to be. So if and only if, for all C, which is a positive real number, and N0, which is a positive integer, there exists n greater or equal to N0 such that the f of n is greater than c times g of n. So don't let this look a little spooky to you. Remember, I told you in the original game plan was we found c and we found N0, and then we checked if the inequality would work for those values. Now, in this one, imagine if I gave you any c and any N0. So they have to be, these are not constants anymore. They can be whatever possibly is necessary to make the inequality work. So I'm just going to check for all possible c's and N0s that there exists. Now, you got to think of n like the constant this time. So now you got to pluck off a particular value of n that's bigger than or equal to any N0 that I can give you. So remember, I can give you any C and any N0, and your job is to pluck off an n, just find me a constant n, such that this inequality holds. So this is the negation of the original inequality. So the game plan is flipped. So I took the whole table and I flipped it over, okay? So I'm going to show you an example of me applying it. So there's two different approaches you're going to find. So approach one is, so the first approach that typically people will use with this definition is prove it directly. So just use this negation of the big O definition. So just prove it directly using this. For those that are a little bit more trained in discrete mathematics, this might look like, okay, well, really, it's kind of just doing the same thing, kind of, just in a different way. But for the purposes of this class, I'm going to show you two different approaches. You get to pick which one you like more. But remember, you still got to do it correctly. So all I'm going to do is I got to follow the game plan here. So you're going to find that the n I pick has to be in terms of c and N0. I can't just, like I did before, where I just pick one and then I kind of solve for N0. I can't do that anymore. What I have to do instead is I got to look and try to find an n that will just simply give me that right value of n. So I need to find that n, and it's going to be in terms of N0 and c. Because remember, c and N0, you got to imagine me kind of hiding behind, like imagine I'm just some weird creature just hiding underneath the table. And that creature has two pieces of paper and has the c and the N0 that they want to give you. Then your job is to, no matter who that little gremlin guy, like me, underneath that table comes up and says, hey, look, here's c and N0. Your proof better work. That's the point I'm saying. So your job is to give me an n. So here's an example using this first approach. So show n squared over 2 is not big O of n. You can see right off the face of it that this is in fact a true statement. However, if I switch these two around, the answer, yeah, it would be true if that n is big O of n squared over 2. But here, this is definitely a true statement. So now I'm just going to give you the game plan. So remember, imagine me as a gremlin hiding underneath the table. So remember, I have my C and N0. Your job is to make it so no matter which C and N0 I give you, your proof better work. So the first part of me is describing me as the gremlin underneath the table, telling you what I'm going to give you, okay? So let C and N0 be arbitrarily chosen and fixed. So this is me underneath the table as a gremlin, and you're sitting up here studying, and then Dad comes out from underneath the table, is like, hey, up here. Here you go, there's C and N0. Do something with it, okay? So your job is now, I've given you C and N0, which are arbitrarily chosen. Remember, I give them to you. You don't know what they are. They're arbitrarily chosen, and then they're fixed. So now you can imagine you have C and N0 to play around with. Okay? That's what this term means. So, here we go. Here's the game plan. We need to find n greater or equal to n0 such that n squared over 2 is greater than c times n. Remember, I don't know what c and n0 exactly are. They can be any of those values. Okay. Notice that, this is me just doing a little bit of massaging to the statement. Notice that n squared over 2 is greater than cn. Remember, I'm not saying that the inequality is true. I'm saying I give you this statement, and now what I want to do is I want to do some massaging to it so I can reveal something about it, right? So notice that n squared over 2 is greater than c times n if and only if n over 2 is greater than c. How do you get this? Well, if you divide by n on both sides of that inequality, the left-hand side, right-hand side, you just go, I divide by n on both sides, I end up with n over 2 is greater than c. Which I can do. Okay. So I have this to play around with. So now all I have to do is just move this 2 up here by multiplying by 2 on both sides. So, implying n is greater than 2c after multiplying both sides of the inequality by 2. So now I have n is greater than 2c to play around with. Okay. So now I have something about 2c. So if I can make n bigger than this, and remember n is an integer. Remember, it can't just be a real number. It has to be specifically an integer. So real numbers contain the integers, but you gotta make sure it's an integer. So we need to do something there. So now if I pick something just slightly bigger than this that's an integer, plus I make sure I satisfy this inequality here, that n is greater or equal to n0, we're done. Okay? So remember, I don't know what c and n0 are, but what we can do is we can say this now. Okay, so I'm going to tell you how to pick n. So pick n is equal to the maximum. So I'm going to use a max function to pick the larger of these two values. So max of n0 and the ceiling of 2 times c plus 1. So the way the max function works is very much like in a programming language. I give you arguments, so these in case numbers, and then I pick the larger of, say, these two here. If I give you 3, it just gives you the largest of the numbers. So n0, remember we need n0 here because n has to be bigger than or equal to n0. I don't know what n0 is. And I know that for this to get violated, I know that n has to be, if this has to be true, I should be very careful here. If this is true, then n has to be bigger than 2c. But 2c might be not an integer. So I'm going to use a ceiling function here. So I'm going to apply the ceiling to 2 times c. Now the ceiling, written like this. So if I give you the ceiling of x, you can just think of this as round up to nearest integer. So that's the ceiling. The floor, by the way, so this is called the ceiling. So like the ceiling, you round up. The floor, but just for the sake of clarity, the floor, which is written with two brackets that look like L's but flipped in, just like this is upside down. This is called the floor. The floor is where you just round down to the nearest integer. So this is where you round down. So you round down in the floor, ceiling, you round up. So I'm just rounding the 2 times c up to the nearest integer up. So I can guarantee this is an integer. Okay? So now look, if I pick this, no matter what c and n0 are, because now it's in terms of n0 and c, this inequality is going to get satisfied for this particular n, okay? So I picked it big enough. Then we have n greater or equal to n0, and for this value of n, the inequality is satisfied. Therefore, n squared over 2 is not big O of n. And we're done. Isn't that cool? So remember, the game plan is just to select I need to select an n, so that no matter what Gremlin Dan underneath the table gives you, it will work and satisfy that negation of our original negation of our inequality. So we're going to do one more example. I'll show you the second approach. Some people like the second approach a little bit more because it doesn't necessarily require you to memorize the original, the negation definition. So I'm cool with you using either of these two approaches, assuming you do it correctly. But anybody that's prosed and knows a little bit more about logic knows that really I'm just doing the same thing, but doing it with a different setup. But don't worry about that. So the whole game plan is I find that n such that it satisfies this inequality no matter what c and n0 are. Now, here's what the second approach is. So approach 2. Here's approach 2. We're going to use a proof technique called contradiction. Proof by contradiction. So here's the idea in contradiction. Assume, like at least in our case, this is how contradiction goes. So assume f is big O of g, is big over big O of g, and try try to show it leads to a contradictory statement. Now, if you don't know what a contradictory statement is, all it means is that it's a statement that is never true. So it contradicts itself, okay? So here's the example I'm going to do with you. So we're going to show n cubed is not big O of n squared. Which is pretty nice. This is indeed a true statement. So here's how we're going to do it. We're going to assume, so that we can get a contradiction, so assume that n cubed is big O of n squared. So I'm just going to assume that this is true here. I'm going to assume that that's true. Then, what does that mean? Well, by the definition, we're going to use the definition. That's it. That is equivalent to me writing this. Then, there are constants C and n0 such that for all n greater or equal to n0, n cubed is less than or equal to c times n squared. So I'm just going to go along with this and see what happens, okay? So since n is greater than or equal to n0, n is positive, right? N is positive. So we can divide both sides of the inequality to get n is less than or equal to c. Right? I've just divided both sides by n squared. N cannot be less than or equal to c for all n greater or equal to n0, because what? Remember, c is a constant, right? And n isn't a constant. Because n is not constant. N is not constant and grows without bound. So I know that this inequality just ain't gonna cut it, right? So now I gotta give you the n that will give me what I want. You'll see how both approaches are gonna ultimately give me what I want. So now I've set up everything. My job now is just to imagine I blew up the balloon. So imagine I have a balloon and I'm blowing it up, just following along with my assumption. Imagine I'm blowing up the balloon. My job now is to prick the balloon to yield the contradictory statement. So I've set up everything. Now I just gotta give you the n, and then we're done. Hence, for example, remember, I just need one example. I need to find that n. Hence, for example, if n is equal to the max, I'm just going to use the max function again. Now, remember, c can possibly be a not an integer, so I'm going to round it up. So I'm going to take c, I'm going to round it up. And remember, it has to be at least the size of n0, which we know anyways because that's a part of our assumptions here, that n is greater or equal to n0. But I just want to make sure I pick the n big enough. And now all I'm going to do is I'm going to add 1 to this. So I just take this, I round it up. So now this is going to be at least equal to, it's going to be either c or bigger than it, but I'm going to push just a peg over so that it's guaranteed to be bigger than c when I pick n. That's what this plus 1 here is for. This value is larger than or equal to n0, but is larger than c. Hence, violating n is less or equal to c for all n greater or equal to n0, and we have derived a contradiction. So there's no way that you could assume that n cubed is big O of n squared while simultaneously having this happen at the same time. That's the big point. So I've given you n such that it violates this inequality. Then on top of that, it's going to suffice the definition that's going to violate our assumption. So you can't have this true and this true at the same time. It's never always going to be false. Okay? That's what we mean by a contradictory statement. So I assume that n cubed is big O of n squared, and I follow through my line of reasoning by massaging things, by just invoking the definitions. Then I pluck off n, and then I just simply say, okay, well look. For this n, it's going to violate that inequality, but that inequality had to have held for all of those values, right? Which yields a contradiction. And we're done. See, isn't that too bad? That's not too bad. So, I think this is the perfect place for me to stop. So, next day, what we're going to do is we're going to talk about, let me just think. We're going to talk about some properties of big O. And then we're going to start analyzing some algorithms using some of the things that we've done so far. Okay? So I want to say thank you very much for your attention. And hopefully, if you have any questions about this stuff, don't hesitate to ask. Okay? So thank you so much and have yourself a beautiful day.